Hello, today we have this problem from a subscriber. So essentially, f of x is differentiable in this interval, and f of 0 is equal to 0, and the absolute value of the derivative is always less than or equal to f of x. Well, let's work with this. So first of all, we know that f of 0 is equal to f prime of 0. That's going to be equal to 0. Now, another thing we know is that absolute value of f prime of x is less than or equal to value of f of x. And that is on the interval from 0 to 1. Let's include x here. Alright. So this is what we have been given. This seems like a proof by contradiction. So let's say there exists some y belonging to this interval, such that f of let's say f of x, no, f of y, yeah, is greater than 0. We know for sure that this function is a non-negative valued. So now what we can say is by the mean theorem, there is some a between 0 and y such that f prime of a is gonna be equal to f of y over y. Now, what else can we say? Well, recall how the absolute value of the derivative is less than or equal to f of x. Well, we can safely say that f prime of a is greater than or equal to f of y over y. Now recall how we're working on this interval. So y lies somewhere here. It's not 0 for sure. So another thing we know is that well, will be greater than or equal to f of y, yeah? And then we can continue this process, narrowing down the interval. And if we were to look into this visually, there were two cases in total. It could converge to some point, like here for example, and since we're constantly dividing by this points, the function will go unbounded. We call how it's continuous. Or if that's not the case, then well, wait a second, I'm thinking. Well, we're constantly being between 0 and y, yeah? So again, this interval is shrinking. However, yeah, it's shrinking, it's monotonic, but it's still bounded, so it will converge for sure to some point. It'll be unbounded here. Now, how do we write this down more rigorously? Well, let's define a sequence, Tn. Let's say that the range of this sequence is a subset of this interval. Good. Now, even better would be to completely disregard the 0 here. Okay, now I think we could include it. I just might have to write a bit more. Anyways, this is substitute this interval. Next, what we have to say is Tn plus 1 is less than Tn, and what else do we have to say? Well, f prime of Tn, f prime of T1 is greater than 0. By the absolute value. Okay, now working with this, that would imply that well, exists a so we'll write down like this, less than T1, such that, okay, actually I'm being stupid. Let's work with the actual value of f, not the derivative. I don't know why I jumped to that instantly. Okay, there is an a between T1 and 0. F prime of a is gonna be equal to f of T1 over T1. It's gonna be greater than or equal to f of T1. Now let's say that T n plus 1 is gonna be, okay, no, let's reform everything here to just n. Alright, now let's say that a is gonna be over Tn plus 1. So f of Tn over Tn is gonna be f of f prime of Tn plus 1. It's gonna be less than or equal to f of Tn plus 1. Alright, so we can say quite a few things, I suppose. First of all, okay, it would be helpful to show that it would rise in a rather aggressive manner. Okay, so f of Tn over Tn is less than or equal to f of Tn plus 1. And next what we can do is we can say it safely that f of Tn is less than f of Tn plus 1. Furthermore, can do is f of Tn plus 1 over f of Tn is going to be greater than or equal to 1 over Tn. Alright. That's helpful. Now, let's define another sequence. Let's call it S of n, and let's define it as f of Tn. Now we have shown previously that Tn plus 1 is less than Tn. Another thing we have shown is that for all n, Tn is going to be greater than 0. So it's bounded. It is monotonically decreasing. So Tn approaches something. Let's call it capital I for pathos. Alright. I mean, I haven't shown that. Okay. All of this is supposed to begin with the assumption that there exists some number y like this. I mean, we have already. Okay, yeah, I have practically said that already. I just need to say that t1 is equal to y. Right, now it works. Okay, so Tn approaches I, yeah? That's what we know for sure. Another thing we know for sure is that we have a sequence as n. And, well, the ratio test does conclude the divergence because only for t1 it could be equal to 1. However, for any other t with the n's greater than 1, t n plus 1 is less than 1 for sure, which implies that 1 over tn plus 1 is greater than 1. So essentially, the limit as n approaches infinity of as n is gonna be equal to positive infinity. And thing is, again, this is convergent sequence, so f of I is pretty much a big trouble for us. This is a discontinuity. So I mean, I could note down more rigor, but I didn't see the purpose of it. I have practically shown everything that is required to prove that there's a discontinuity implied by the existence of some part of the function that is not like everyone else, is above 0. Because then there is another part, and it converges, and then we get a divergence. Okay, that's it for today. Bye.